Now let's first briefly recap what we learned about statistical ensembles and free energies in either Statistical Physics 1 or in Physics of Life 1. Well, what we have to realize is that all biosystems are embedded in an environment that is given and set to a certain temperature. Hence, the ensemble that we should use in order to describe the system in the sense of statistical physics is the canonical ensemble. The partition function of the canonical ensemble, Z, depends on three parameters. It's n, the number of particles, it's beta, the inverse temperature, and the volume. Now, given such a system, we learned in statistical physics what are the equilibrium conditions between two separate systems that you bring together. The first is the chemical potential mu. Chemical potential is defined by the log derivative of the partition function with respect to the number of particles n, and is given by that this the derivative is equal to minus mu kb. The second is the temperature, which in the case of the canonical ensemble is set by the temperature of the bath. And the last is the pressure. Pressure P is again given by the log derivative of the partition function, but now with respect to the volume. And this derivative is displaying pressure divided by kBt. Now, in statistical physics, we learned if two systems are in equilibrium, those derivatives have to be equal. Now, let's look into an example that is important also in the topic that we will discuss in the following. And the example is the ideal gas. So the ideal gas is a gas of particles that do not interact. The partition function of an ideal gas, we calculated many times. It's given by Z of n, beta, and V is equal to the ratio of the volume per particle and the volume characterized by a typical length scale, the thermal de Broglie wavelength of that particle. Now, the thermal de Broglie wavelength is a characteristic which depends on, for example, temperature, but also on the mass of the particles. And it's given by the thermal de Broglie wavelength squared is equal to h squared divided by 2 pi m kBt. Now, we saw that in particular the logarithm of the partition function plays a major role in defining equilibria. Hence, it's a good idea to just take the logarithm of the partition function, leading to the expression that the logarithm of the partition function is equal to n times the log of the volume per particle minus the log of the third power of the thermal de Broglie wavelength. Now, having the partition function, we now can calculate the chemical potential of an ideal gas as given by the log of the partition function, the derivative of the log of the partition function with respect to the number of particles, and we obtain that mu is equal to minus kBt times the log of the volume per particle plus the log of the thermal de Broglie wavelengths to the power 3 plus 1. Now, in our further discussion, we forget the constant plus 1. Hence, the chemical potential we can rewrite, and it will read that it's equal to kBt times the log of the concentration, as the concentration is the number of particles divided by V, plus a constant mu0 which is the standard chemical potential, which is dependent on the temperature, but also on the kind of particle, because the mass is included in here, and chemical energies due to a reaction of two particles. Where you know from statistical physics, in the physics world, people like to talk about the partition function. Yet in chemistry and biology, ensembles are expressed as free energies. We learned in Statistical Physics 1 that there is a direct link between an energy representation and the statistical physics partition function relation. And there we found that for the canonical ensemble, the respective free energy is the Helmholtz free energy, F, which depends on n, the number of particles, the temperature, the volume, is equal to E, which is the inner energy of the system, minus Ts. Or with respect to the partition function, the free energy is equal to minus kBt times the log of the partition function. Now there are more free energies. And actually for chemical reactions, or also for biological reactions, it's more handy to express the values in terms of the Gibbs free energy, which has the free parameters, n, the number of particles, the temperature, and the pressure. The reason for that being that volumes might not be constant. A cell can change its volume due to osmotic pressure, for example. But the pressure on the outside world is a constant. Hence the Gibbs free energy is a typical representation, energy representation of a system for biology. So in order to obtain the Gibbs free energy, we have to apply one additional Legendre transform, and the Gibbs free energy is then given by E, the internal energy, minus Ts plus PV. Now, for homogeneous systems, we know that the internal energy is given by Ts minus PV plus mu n, which together with the two Legendre transforms shows us that the Gibbs free energy is nothing else like mu times n, the chemical potential. Hence our take-home message here is the Gibbs free energy describes the chemical potential of a biological system that is at constant temperature and constant pressure. So let's wrap up this part. What we have to state is that biology is driven by chemical forces. The chemical forces are characterized by the chemical potential, where the chemical potential mu is given by two terms. First, kBt times the log of the concentration plus mu zero, the standard chemical potential, which describes a certain chemical reaction and also the molecules involved, and is dependent on temperature. Now, by calculating the chemical potential from the derivative of the log of the partition function, we will first split up products in the log of the partition function into the sum of the logs. We come into actually a physics problem, ending up in terms of units, that we have now the log of a concentration. Now, chemistry has a simple way out of this, and in chemistry, what is done is the concentration is divided by the standard concentration as defined by 1 molar or 1 mole per liter, and in that case repair what we neglected in the beginning. Now, doing so, we obtain a properly defined chemical potential, and we have the definition of the standard chemical potential mu zero given by epsilon naught, which is the energy in a chemical reaction, minus 3/2 kBt log of 2 pi m kBt divided by h squared. Further, we realized that the change in the Gibbs free energy is nothing else than the chemical potential times the change in the number of particles in the system.